So here we are back again with more Commodore 64 Games memories. This is about the different versions of Wizball that I discovered while I was working on the technical deep dive. I also cover how I would have reverse engineered the original tape loader that I got for Wizball when I purchased it from John Lewis way back in the older time. So let's get into it. Here we are in my usual ICU debugger. First of all, I'm going to run the Ocean Wizball tape file, which should be the original Ocean software release from 1987. This is the version that I actually purchased way back in the dim distant time. It has the normal kind of what you would normally expect for an Ocean release. It contains some music title screen, and then it runs the game code. As was fairly typical for games of this era, the game used a turbo loader. It was an auto booting turbo loader as well, so even if you did L-Shift-O, the tape code would automatically start no matter what you were going to try and do. Here I saw that the tape loader code had already started working, you can see, because the screen has become enabled, the border has gone black. I'm just using the ICU debugger, well, the Acme monitor disassembler, to show the code, and you can see here that it's looking for something changing in 0 page location 2, 02 rather, which is the same. And this location in 0 page seems to be like a flag which indicates when a chunk of turbo saved data has finished loading, and we can see here that it's loaded some extra code up at 800 onwards, and actually this code has a little message saying, "Hello there, hacker, what are you doing trying to break in? This program isn't gullible to your limited 6502 capabilities. Lots of love, Paul H. Master of the CIA." I'm guessing this message was added during the mastering process. It was quite usual for Ocean to have different people or different teams, sometimes even outside contractors, that would provide these kind of mastering capabilities for finished games. Games would be on disc and also on tape, and sometimes the programmer would do a complete disc version, maybe without protection, and then they might allow the disc version to be used in some way to provide the tape version. So you can see here that different chunks of memory, say for example the sprites in RAM up at D000 roughly, would be loaded first, and then the music would load and then start playing. The bitmap data then starts getting loaded, and then the bitmap data starts being loaded and being displayed at the same time because it's loading the bitmap data into RAM in the visible bitmap area. When this came out, when I was quite young, probably around about 14 years old at the time, I was really interested in how the code, no matter what it was, what I tried to do, would auto boot and it would enable the screen. And I was very interested at the time in tape turbo loading technology. We can see here that it's just running through some of the title screen management and bootloader code and music playing code here. So this little chunk of code, which was loaded at hex 800, is just running through various different stages of loading different chunks of data, and then the management code, if you like, just runs through different memory copying routines and or playing the music. So it's just loading different chunks of data from tape and stuffing it into the correct part of memory. Now, when the game actually wants to load the final chunks of data, it has to turn off the music because the music doesn't want to play anymore. Because it can't, because the music is being overwritten in memory, so the music has to stop. The screen has to be disabled because we don't want the bitmap being displayed anymore, because the game code needs to replace the bitmap, the loading screen bitmap, in memory. We can see at 959 in hex that it clears the SID registers, probably after it's finished loading. We see a jump to 103 in hex, the I'm thinking at this point in time that the jump to 103 in hex is going to be the last part which loads the last little bits of data to allow the game code to replace all of the stuff in the screen that you can see here, the loading message, and also the loading management software, which is at 800 in hex, which also contains the hacker message, or the hello there hacker message. So the last little bit, once the breakpoint triggers, here we go. I'm going to have a look at this code. We can expect the hello there hacker message to get overwritten. It's the usual kind of thing. It's updating some values up in the turbo loading code. We then have a load A with hex 2 from 0 page, and then branching around until the last chunk of data has finished loading. And then it signals it wants to load the next chunk, and it waits for that to happen for a few times. So here we can see that it's finishing the loading of the data over the music routine, for example. It's loading the final sprites up at C000 in hex, which is the last bank of the VIC memory. It should, in theory, start loading the final data up in the screen area and also the loading management part of the software. And then we see that it's doing a final jump to 6389 in hex. 6389 in hex is basically the game entry point. This is where the real game code starts. So luckily enough, in all of the versions, the game entry point address is consistent. So what I can do is that if I'm trying to, hack or try to package this game, or trying to compress it into a single program file, what I could do is that I could choose to stop execution at 6389 in hex using a breakpoint in Vice, and then save out all of this data to a great big file. So from, say, for example, 0400 in hex to FFFF, and then compress it later on. Using Vice, of course, it's very easy to do that because Vice has a nice integrated machine code monitor. But back in the old day, I did not have a hacker cartridge. I just had my base machine, and I had a programmer's reference manual and a book on machine code, and that was it. I had to figure out how to reverse engineer all of this loaded code myself. Now, starting this load from the beginning, when it displays the file name, we can see that it's already loaded some data, and this is data which is it at 33C in hex, which is the tape buffer, or tape loader buffer. Tape buffer, basically. It's up in upper 0 page memory. Here we are, the tape IO buffer 33C. Now, if we interrogate the tape buffer, we can see it has some data type, which is 3 or something like that, and a low and high address of where it's going to load data to, and a low and high address of where it's going to finish loading data. So it's going to start loading data at 2A7 in hex and finish at 334 in hex. But we can see here that we've got the file name, we've got some extra data, and then we have what looks like code. Really interesting, huh? So because the tape buffer is so large, there's a lot of extra space, and the Commodore 64 has saved out this and loaded it back in again. So actually some of the code which is used for the turbo loader can be stored in the tape buffer, because once the file name is displayed, the tape buffer is left alone practically. It's not really used apart from the low and high start and end address of where it's going to load the rest of the file data. While loading the file data, the tape IO buffer is left well alone. So we can use this for permanent storage, if you like, of some data or some code. Now we know it's going to be loading code at 2A7. What does this mean in real terms? Well, in 2A7 is actually a whole bunch of 0 page addresses, upper extended 0 page. There's some unused data, but then we have a whole bunch of vectors. We can see here that there's a whole bunch of basic type vectors, there's a whole bunch of kernel vectors, there's some temporary storage, and so on and so forth. Now, changing these vectors while the tape is loading can cause the kernel routines for loading data from the tape to do some unexpected but some desirable things. We can, for example, tell the kernel code that we want to finish loading early. We don't want to verify the data that we've loaded. We can tell the kernel, we can tell the basic part of the operating system that we want to start executing our own code. We don't want to execute a basic stop routine or a basic line chain routine. If we want to try and load this data that is going to come in and try to auto start the code, what we can do is that we can alter the start and end address actually in the tape buffer while it's displaying the file name, and we can tell it to load the data that would have gone over the vectors into, say for example, the screen memory up at 04A7205534. So that's what we're going to do, because it loads the tape loading routines will read the start address after you press the spacebar to continue loading the file after displaying the file name. So what this allowed me to do back in the old days was to stop the auto starting tape loader code and to then start investigating and interrogating what the logic of the code did. So once the code was loaded into screen memory or anywhere else that I wanted it, I could then use a disassembler to inspect the code. So this is what I used to do in the old days. Of course, in the old days I didn't used to have a hacker cartridge or anything like that, so I wasn't able to break into the execution and to change the tape buffer contents by hand with a machine code monitor like I can do here. I used to have an extra interrupt, the IRQ interrupt that I would claim, which would then do all of the address rewriting in the tape buffer work for me, and it would do that once only. So I'm going to show you how I would have done it in the old days in a minute. But what I'm doing now is that I'm having a look at the code, I'm investigating what it would do, and I can see here that it's setting up some addresses at FFFA and FFFB. It's altering CIA2 timer low and high values, and FFFA and FFFB are, of course, the non-maskable interrupt, the NMI service routine addresses. This means that actually this auto-booting tape turbo loader code is doing a little bit of a trick where it will start a counter which will eventually trigger a non-maskable interrupt. It also sets up an IRQ at 35, or to execute at 351 by using the vectors at FFFE and FFFF. So it's actually setting up two interrupts, the non-maskable interrupt and also the regular interrupt, which is set to run on the edge of, say for example, the tape pulses coming from the tape. So the loader interrupt, which is on the normal IRQ, does all of the work of loading bytes, turbo data bytes, and storing them in memory. The NMI interrupt is used as kind of like a little protection check. So what it does is that, so the NMI code actually jumps back into, well here I'm actually looking for the address, and the address actually jumps back into the loaded tape IO, the tape buffer code. So we can see here that the code from the NMI then goes into here, it clears the interrupts, which allows the IRQ to start, and the IRQ loads the tape bytes. But it's actually using the MI to jump back into the tape buffer, and then this tape buffer stuff self-modifies some of the code back in the auto-booting tape loader code, and then it jumps back into itself again. And when it jumps back into itself again, it starts running a slightly different state machine because it's self-modified the address. And what it does is that it tells it eventually to jump back into the boot management of the loader management code, which is at 800 in hex. we can see that it was actually loading the hex value of 2A7 into the vector at hex 302 and 303. This vector is one of the basic program starting vectors or line chaining vectors or something like that. Basically, once data finishes loading, the kernel routine will call this routine to say, whether or not it wants to have a look at what is the basic program that's just loaded. There wasn't a basic program loaded, it was auto-starting data. And the auto-starting data starts because of the vector that was changed at 302 in hex. This kind of usage of the vector at 302 in hex is a very standard way for a lot of tape turbo loaders to actually get their code to start working. There are some other different variations. Sometimes they use a stack slide, sometimes they try and claim one of the IRQ vectors. But basically it's a similar kind of methodology. You rewrite the vectors to get your code to start working. Now, back in the old days, it took a long time to reverse engineer this kind of program flow because it's very non-standard. It works, but it's very non-standard. But luckily enough, I worked on a tool to translate tape files and to try and work out how they would auto-start. Basically, it takes all of the knowledge that I have of how auto-start code would work in the various different variations that I could find, and then it would output its best guess. The integrated Vice debugger, of course, makes all of this work a hell of a lot easier than it used to be back in the old day. Back in the old day, there used to be all sorts of traps and gotchas and timers and NMI interrupts and all sorts of, double checking that you haven't altered code by EORing it with itself and using that as a de-scramble check, if you like. So here I'm showing you how I use my tape tool to inspect the data that's actually inside the tape file. It says the code will attempt to load data at address 2A7 in hex. It shows you what the data is. These first bytes here are tape data countdown bytes. The kernel doesn't put those into memory, it puts the rest of the bytes in memory. We can see here actually is that during the loading process, I think during the loading process on this variation here, it resets the IRQ vector back to the default value to what it should be. And when it does that, it causes the tape code to early out and then to execute the vector at 302 in hex. Because the kernel tape loading code, if I remember correctly, checks to see whether or not the loading has finished by checking to make sure that a different part of the code, the data loading code from tape hasn't restored has restored the vectors to their default value. So EA31 is the normal IRQ vector. The rest of the data puts 2A7 actually into several different vectors, just to really try and make sure that 2A7, you can see here that 2A7 is actually, or A702, which is low high, is actually found in a few different places because the data wants to really make sure that some of the vectors it wants to claim are actually claimed, just to really make sure that the kernel and the basic portion of the operating system really does run the code at 2A7 in hex. So here, after a hard reset, we can see that we know that the tape buffer is going to be basically at 0. Nicely cleared. So you're thinking, yeah, that's all great, Martin, but how would you really have done that back in the old day? Because it looks quite complicated. Well, here's how I would have done it. I would have used my assembler, or I would have hand assembled by memorizing the opcodes, as you would normally do with machine code assembly language in those days. I would have put up a little routine, say at 49152 in decimal, which is C00 in hex. I would have put up a little routine up there, which sits on the IRQ vector, and I would look for the high byte of the low address equaling 2 in the tape buffer, and if it is, it will go and do some other stuff. If not, it will just jump through to the normal EA31 IRQ vector. I would then have the start load address incremented by 2, and I would store it back, and I would take the end address and I would add on 2, and I would store that back into the tape buffer, and then I would also jump back to the normal IRQ vector. I would have code that looks like this, way up in memory somewhere. I would then point the normal default IRQ vector at 314 in hex to my hack routine, if you like. I would then start the tape loader as normal. Now the hack routine, because it only runs in the IRQ when the screen is visible, I know that it's running when the screen is visible, when it's displaying the file name. And there we go. Because I've modified the tape buffer, the tape IO buffer, during the file name display, during loading, I know now that it's redirected the data it would have loaded over the vectors actually into the screen memory. Now once it's into the screen memory and it has stopped at this point, I am free to then load or save it to somewhere for later analysis, including the tape buffer. I would then analyze it in a disassembler, or I would hand disassemble it. I would probably just use a disassembler, to be honest, and then I would print it out and then I would mark down all of the specific stuff that I'm really interested in. I would see that it's using IRQs, I would see that it's using NMIs, I would see that it's using a timer to basically break out of this infinite branch and not equal loop back to itself. This tape auto boot turbo loader actually doesn't do too much protection. It uses an NMI on a timer, but that is the limit of its obfuscation. Actually, in my own tape turbo loading bootloader stuff, I would use more obfuscation. I would use some descrambling, and I would put that on an NMI timer, and I would have clearing of memory going on at the same time as the NMI timer, just so that if anybody was really messing around with the timer, then I would trap that and it would fail to actually work properly. But this, auto booting tape loader code wasn't that complicated, to be honest. Once you've got control of the machine, and once you understand the boot management software and how it actually works, because there's this hacker message, you can actually add a whole bunch of extra code all over the top of the hacker message, and you can control the machine all the way through the loading process. So actually saying hello hacker messages and stuff like that actually makes it a lot easier to intercept. And of course, you work through by trial and error eventually to the point where it's going to be getting through to the same game entry point at 6389. And of course, once you've got it all the way through down to that point there, you are then free to find a very small number of bytes, usually on the stack, from 100 in hex to 1FF in hex. And you would just bank in the kernel. You would save out all of your individual chunks of memory in all of the RAM. Basically, doing what I'm doing now is that you just do this. You would save out all the memory, but you would have to do it in chunks because you'd have to copy around stuff and copy around chunks of memory and stuff like that. You would normally save it to disk because that would be a lot easier. Once you have all of the chunks of memory, it would then be a pretty trivial job to then patch it all together and link it all together. Because as we saw, the tape turbo loader code uses 0 page, it uses the stack, and it uses the memory addresses all the way up until about 380 in hex. Probably 3FF, and then you just patch it all together. So once you load it back again, you can just run the game as normal. The game thinks it's loaded from tape, and then everything's fine. There shouldn't be any extra there wasn't any extra protection checks, if I remember correctly. Not for this game anyway. Other games sometimes would, but in this case there wasn't. So that was the original Ocean Sensible Software tap file. There was also a Hit Squad release, which was actually noticeably different in terms of how it loaded. But using the data that was saved out, so all of that memory from 400 hex to FFFF, I could then use my own tools for linking that code together and actually running the correct execution address. My compression tool is actually very efficient. It produces quite a small file for the whole game data that was loaded into memory. I can then just run that file just to really verify that it really works, and of course, yes it does. We can see it's doing a very thorough job of decompressing all of the memory. You can see here that it's the memory in the first screen bank is actually the memory that was loaded in during the ocean load. An interesting thing to know here is actually the screen memory indicates that the person who mastered the ocean version of the tape file loaded the data from disk, because you could see a list command and the start of a directory listing of a disk drive up at the top of here. You can see the highlighting it in the memory view here. You can actually see that it's got the start of the Wizball directory listing title here with the L-Shift-I list command up at the top of the screen memory. So anyway, that shows that the compressed game hacked from the original tape, hacked in inverted commas, works. So I saw the Hit Squad version of Wizball. Now, because we know the game entry run address, which is 6389 in hex, we can just put a breakpoint there. We can load the tape file, and then we can let the breakpoint hit, and we can save out the data from 400 in hex all the way to FFFF in hex. And we can do a similar thing, but with the Hit Squad version. Now, here I'm using the Tape Tool Analyzer tool to analyze the Hit Squad original tape file, and I can see that the data that's in the tape I/O buffer that would be loaded is different to the data that was in the original Ocean release. It uses a slightly different turbo loader. This is kind of to be expected actually, because if you watch the Hit Squad release as it's loading, it doesn't display a title screen. It just displays a block countdown message. Looks like this. So the screen is off, but we get loading color bars. It's loading the boot management code here, which is Hit Squad presents blah blah blah, and then it's doing blocks to load, and it's loading a ton of extra data lower down in memory. We can see from the memory view it's just filling it from bottom to top. I've enabled the warp mode here in the emulator. That's why it looks a lot quicker than normal. We can then see that it eventually runs a whole bunch of code in very low 0-page memory, and then it jumps eventually to 80D. So we put a breakpoint on there just to see what the data at 80D looks like. We can see from the sprite data that it's loaded some very loosely compressed sprites. Probably some variation on run length encoding by the looks of it, because it's mostly recognizable, but it's also compressed slightly. The sprites are all out of alignment. So 80D is 2061. 2061 is a very standard sys start address. It's basically a address in memory which is just after a sys command at the beginning of a basic program, which is normally 801 in hex. So here we go. We let it run until we hit the breakpoint for the game entry at 6389, and it basically decompressed a whole bunch of data in memory, as we can see from the sprites, and then the game runs. Again, we can breakpoint at 6389, and we can save that file, and then we can compare the decompressed game data for the whole of the 64's memory between the Ocean and the Hit Squad release, and that's what we're going to be doing now. The Ocean release is the original one, and the Hit Squad release is the later one, which was out about a year later or something like that, maybe a bit sooner, maybe a bit later, who knows. Well, we can see, using Beyond Compare, which is an excellent tool, that the very start of memory up near the top of the screen memory is a little bit different, and there's a byte difference here, and there's a byte difference there, but most of 99.9% of the memory is identical, apart from the chunk of data right at the end, which is the very last few banks of upper memory, which is basically the last character set in memory, which when the game title screen starts running, it's actually not used that much. And it doesn't really matter, because that's the game character set which is decompressed for every level in the game. Anyway, so here I'm actually running two versions of ICU side by side, and I'm showing the character sets in the last bank. And I'm going to run the Ocean release in the top, and I'm going to run the Hit Squad release in the bottom, and you can see that there are very minimal changes and exactly what they look like in terms of the character set data. I'm going to put a breakpoint, which is the game entry point, of course, at 6389 in hex, or both of them, because we don't want the title screen to be running when we're doing the end of memory character set comparison. So this is the Ocean release. As it was loaded, the Ocean release, remember, plays music and also displays the game loading screen. The Hit Squad release just displays a text screen with a countdown, the blocks that were loaded. It doesn't play any music or anything else like that. You can see how the sprites are only different in the last few sprites. And of course, the sprite and the character set data are in the same amount of same place in memory, so we can see how the last few pages are different between the Ocean and the Hit Squad release. And the Hit Squad release is probably like that because while it's decompressing, it moves everything, it moves the compressed data right up to the end of memory, and then it decompresses. So the last few pages in memory probably contain original compressed data, whereas the last pages in memory from the Ocean release probably contain default memory data. So those were the differences, not very many differences between the Ocean and Hit Squad release. We can basically see in Beyond Compare that most of the memory is identical apart from inconsequential character set data differences, end of memory differences, and the code is practically identical apart from those few byte differences. So I started looking at different releases. I started looking at some hack releases. So I found this release, which was by Sir 13 or whatever it is, and it contains a single PRG file, single program file on a disk image. So I extracted the program file and I had a look at it, and I could see that it was compressed in a different way compared to the Hit Squad release. The Ocean release is not compressed at all. Here we're going to see what it looks like when the Sir single program file is executed, and you can see that it decompresses a whole bunch of data, just like this. Now, the Sir release, we can see that actually the end of the character set data has been zeroed out. It's nice and blank. We can see how it decompresses using the memory view, and we can see that it does a double decompression, if you like, double pass decompression. But the end of the character set data has been zeroed out, and we can save this using the debugger at the same hex game entry point at 6389. We can see that the end character set data has been replaced once the game level starts, which is to be expected. Every level has a different character set, and it stuffs that at the end of memory. So I compare the original Ocean release, which is in memory, with the Sir release at the same execution address, which is 6389. We can see that the startup memory is different. We can see now that there are actually quite significant changes. But Beyond Compare is telling me at this point that there are significant similarities where sequences of bytes are unchanged. It's just some bytes are changed. Now, these bytes look like, most part, low byte differences. I can see that, say for example, A9FF is load accumulator with the immediate value FF. 8D is storing the accumulator in the absolute address 45CE. I can see that there are strings of opcodes which are identical, and I can see that only some low bytes and some high bytes have been changed, and these low and high bytes reference data within the Wizball code addresses, memory addresses. So this is intriguing. This tells me that actually some portions of code have been moved or relocated from the original Ocean release compared to this Sir release. And the code differences are quite significant, but they're done in such a way as it looks like they are code differences resulting from a tweak of the original source code. And then there is a slightly different assembled version of the source code. So this looks like a different build release version. Now, Recall that the Ocean release and the Hit Squad release are practically identical. This hacked release is using an updated version of the code. Now, it's possible that whoever did this hacked release decided to remove and disassemble and reassemble Wizball code. But we can see that while the code is somewhat shorter in the SIR release, it then regains its synchronization with the original Ocean release just as the high score saved data is coming into memory. So this is intriguing. It looks like somewhere along the graphics data right at the end of memory, some of it is very different, but that's only the last few pages in memory, which are the end character set data, which we already know about, and that can be safely disregarded. The interesting thing here is that there seems to be two different code build versions here. Now, it would be possible to minutely inspect the code differences to see whether or not there are bug fixes, or whether or not it's just a disassembly and rearranging and reassembly done for one of the hack releases to improve compression or something like that. But at this point in time, I was intrigued. How many other different versions of the code can I find in different hack releases? So I looked for other hack releases and compared their code. So I found a release, I think it was done by Crew 1001. Again, that was from CSDB, and I'll put the link in the video description. But this version is a single program file which displays the title screen, then displays the hacker's message, and then it decompresses the game. We can see here it's doing quite a lot of decompression. If we look at the character sets at the end of memory, first of all the sprites and the character set data, here we go, text screens, whoops, character set. We've actually got some graphics data loaded at this point. What we can do is that we can do a breakpoint again in the Crew 1001 version, and we can again save out all of the memory from 400 in hex to FFFF in hex, and then we can do a binary comparison of the Crew release with the other releases that we know about, the original Ocean release and the SIR release, which is what we're going to be doing now. So this is the SIR release with the Crew release, and we can see that practically it's identical. So the SIR release and the Crew release have virtually no differences, apart from the SIR release has better zeroed out the end character set data, whereas the Crew release has not. Or rather, maybe the Crew release has just left original compressed data at the end of memory because it hasn't bothered decompressing all the way to the end of memory, which is perfectly fine. There are some code bytes here which are different somewhere in the screen memory, I think it was, but nothing really of consequence. So the SIR release and the Crew release are practically identical. I think we can say that they are identical in terms of the code that was used to produce the hack release. Comparing the Ocean release with the Crew release, we can see that there were significant differences. So the SIR release and the Crew release were practically identical in terms of code. But they are different, and they have significant code differences compared to the original Ocean and Hit Squad releases. Now, I have confidence in the original Ocean and Hit Squad release because they are basically the original tape files. So again, I'm wondering, where are these differences coming from? So I found this version from archive.org, which is again a D64 file with a single proc. But when I run this, there was no hacker splash message or anything else like that. But when I run the single profile, I can see that it decompresses in a different way compared to the other releases that I've seen so far. So again, I'm intrigued to compare the memory of this at the same game entry point of 6389. The Commodore 64 Basic V2 banner is intact when the title screen starts. Now if I compare the original Ocean release with the version of the game code that was running from the archive.org release, again I see significant code differences, but these significant code differences are different in size and scope compared to the version of the code differences between the Ocean and the SIR release. They are so different, in fact, that in this version we have a significant difference where there is this chunk of text data missing. So the original Ocean release has this text data, which is part of the WizTip screen. Now, this Ocean release has actually 2 copies of the Horizon gives immunity, blah blah blah. The archive or release version strips out this duplicate unused text block. We can see here that the Ocean game actually has two copies of this text in 2 different places in memory. The archive org version does not. It only has 1 copy. So this is crazy. We have the significant code changes between the Ocean and the Sir release, and we have significant code changes between the Ocean release and the archive release version. So this looks like, so far I've managed to find 3 different versions of the code for Wizball. Ocean Hit Squad release, Sir Crew release, and then the D64 archive.org release. And the size and the scope of these code related changes looks like that the Wizball code was recompiled from some kind of source code, or maybe recompiled or reassembled from disassembled code, and things were shuffled around. It isn't just taking memory and just moving it around where it's unused. It's actually used code. The offsets change. There are slight code tweaks and things removed and things added, and then this causes the offsets actually to subtly change. So this is why I think, this is what makes me think that there are at least 3 different original code builds of Wizball, and Ocean and Hit Squad were using an original release version, and then there were other versions coming from elsewhere. So maybe these hacked versions, and I'm thinking that the archive org release is a hacked version. However, it's worth remembering that the archive org release looks like the NTSC release because it only has the lower status panel, which alternates between the pots and the upgrades. But basically the Ocean tape file and the Hit Squad tape file releases are tape releases. Maybe there was a slightly improved disk version, and maybe these hack versions are using disk versions. But then again, the disk version seems to have, if the code differences are coming from disk versions, then there seem to be at least 2 different disk versions, whereas the tape versions have the same code. So maybe the differences in the code from the disk versions come from early publisher builds that were just before the final distribution release, or maybe one of the builds comes from a preview publisher release, or maybe a review copy, and then the other code version comes from the final D64 release version. Currently I've been unable to find the original Wizball D64 release version, so I'll keep on looking for that first. I haven't found an original D64 of Wizball, so maybe that's what it is. Maybe, like I say, maybe there was a review copy that got hacked and distributed first, and then there was the release version, and then the release version had a hack done on the D64 version. So anyway, that's about all that I've got for this. So apart from that, I'm comparing now my compressed version of the Ocean build with Sir release version, which is also a single program file. So you can see my compressed version on the left at 36.9 kilobytes is a lot smaller than the Sir release at 47.1 kilobytes. So there we have it. That was a deep technical dive into the differences between some tape releases, both original and hacked, and also the archive.org release, which was notable because the NTSC code changes look like they were assembled from the original developer source code, which, because those code changes look relatively similar in the way that the code has been laid out in memory, it's just that the offsets, the low and high addresses have been changed. It kind of makes me think that the Sir and the Crew release were also assembled by the developer. It's just that we have probably 2 different developer code builds for the PAL version, and then of course there was the NTSC build differences because the differences in the status panel and the pots. So these different versions are intriguing. I'd like to try and find the original D64 version, so if anyone has the original D64, not a hack of the D64, then please do let me know, because I'd like to have a look at that one too to see if the code is basically the same as the PAL D64, and also if there is an original NTSC D64. I'm interested in looking at that one too and probably comparing it with the archive.org release. So that's about it for this video. It's already quite long, so I'm going to wrap it up right now. If you like these kind of deep technical dives into old Commodore 64 retro games, then please do consider liking or subscribing to this channel, or send me a message on Twitter where I can be contacted. Thank you very much for watching, and have a great day wherever you are.